Calc BC, welcome to 7.2, Taylor Polynomials Part 2. So we are just going to continue with our understanding or expand our understanding of Taylor polynomials in this lesson. If we take a look at College Board's course description, we're still in lesson 11 here, finding Taylor polynomial approximations and functions before we move on to any of the rest of these topics. And just like last lesson, our essential knowledge is the same. Although this probably makes a little bit more sense than it did the first time that we looked at it. The coefficient of the nth degree term in a Taylor polynomial for a function f centered at x equals a is f at the nth derivative of a over n factorial. That comes straight from the Taylor polynomial definition. In many cases, as the degree of a Taylor polynomial increases, the nth degree polynomial will approach the original function over some interval. We've seen that as we add more and more terms with higher degrees to our polynomial, it looks more and more like the original function. And Taylor polynomials for a function f centered at x equals a can be used to approximate function values of f near x equals a. And we've seen that as well, right? Because if you're close to where we're centered, the polynomial is a pretty good approximation for the actual value of the function. It's not exact, but it's an approximation. Okay, so let's switch over to the notes for today. All right, so here are our notes, 7.2, Taylor Polynomials Part 2. The first box up here is just the original definition of Taylor polynomial and Maclaurin polynomial. Once again, no big changes there. So you can read over that. That's a good reminder here for us. And then we have Taylor's theorem. So Taylor's theorem is something new. We're actually not even really going to use this today, but I just wanted to introduce it to you. And this is a concept that we're going to study further on in the unit. But this idea of error is coming back. So to use Taylor polynomials effectively, we need a way to estimate the size of the error. This is provided by the following theorem, Taylor's theorem. If a function f is differentiable through order n+1 in an interval containing c, then for each x in the interval, there exists a number z between x and c, such that here's the whole Taylor polynomial plus r sub n of x, r meaning remainder, where the remainder is this crazy looking thing. And I'm not even going to attempt to read that to you. It's just going to sound confusing, but we are going to study that in depth in a future lesson. So one future or useful consequence of Taylor's theorem is that, the remainder is less than or equal to this thing where we have the maximum value of f n plus first derivative of z between x and c. This gives us a bound for the error. It does not give us an exact value of the error. The bound is called Lagrange's form of the remainder, or the Lagrange error bound. We're going to study this in more depth later. So that's just something to introduce to you, this idea of Lagrange error bound. We're going to figure out what all that means, but it's possible to come up with a bound of the error in an approximation, depending on how far away we are from C, from where we're centered. Just like in the previous lesson, we found the error between our approximation and the actual value. If we don't know the actual value, we can still find the approximation and some sort of error bound to tell us, well, we're about this far away, or we're somewhere in this interval is our actual value of the function. But anyway, we'll come back to that. Today's lesson is just going to ask us to apply Taylor polynomials in a couple different unique and interesting ways. So let's take a look at this first example. Given the second degree Taylor polynomial is a plus bx plus cx squared, and it's the second degree Taylor polynomial, as I said, for f about x equals 0, what are the signs of a, b, and c if f has the graph pictured on the right? Explain your reasoning. So we know we are centered about x equals 0. So we're taking a look right here. And before we think about a, b, and c, let's just think about if we're doing the second degree Taylor polynomial, that means we're interested in the original function value, the first derivative, and the second derivative. And specifically, since we are centered at 0, we are interested in f of 0, f prime of 0, and f double prime of 0. And I don't have any way of knowing what these values actually are, but I can tell the sign of these values just by looking at this graph. And so if I think about the position or the y value when x equals 0, I can tell that we're above the x-axis, so that y value is going to be positive. So f of 0, I know, is going to be positive. The first derivative, I can tell we have a positive slope here. So this is going to be positive as well. And the second derivative, I can tell that this is concave down. So that's going to have a negative second derivative. Right? So now if we think about our formula for a Taylor polynomial from the top of the page. My camera's lagging here. Sorry about that. If we think about this formula, if we think about a plus bx plus cx squared, and we have a Maclaurin polynomial because we're centered at 0. So that a is just going to be f of 0. The coefficient of the x term is going to come from the first derivative, and the coefficient of the x squared term is going to be coming from the second derivative divided by 2. So if we come back down here, what that's meaning is that a is going to match up with the f, b is going to match up with f prime, c is going to match up with f double prime. So what I can say is that a has to be positive, b has to be negative, and oh my gosh, I meant positive. C has to be negative because it matches up with the 3 derivatives, or the position and the 2 derivatives that we found. Okay, so those are the answers there. And I explained my reasoning out loud, so I'm not going to write that down. We do have this work over here to show it. And hopefully that makes sense. Okay, comes straight from the formula. Let's keep going on to the back. Suppose that the function f of x is approximated near x equals 4 by a third degree Taylor polynomial for p sub 3. So the third degree Taylor polynomial of x is as follows. Find the value of f of 4, f prime, f double prime, and f triple prime, all of 4. So what I'm going to do is write out the formula for this third degree Taylor polynomial centered at 4. And then we'll try to see if we can find the missing pieces here. So let's try this. So we have p sub 3 of x. Now I'm just going to fill in 4 for all of the c's. And I'm taking this from the front of the notes or from our previous lesson. This is a formula that you will have to have memorized, but my hope is that since it kind of makes sense when we kind of worked through where it comes from in the previous lesson, hopefully that'll help you not have to feel like it's a burden to memorize. It's just kind of a natural thing. Okay, so I'm taking the x value of 4 for all of the function values. And I'm plugging in 4 for c. Okay, so let's match that up with what was given in the question and see what we get. So I can tell right away that f of 4 has to equal 2 because that's the first thing given. All right, and I'm going to pause my screen share really quick, and I'll be right back to try to mess or get rid of this lag. I'll be right back. All right, I think that helps. We'll see if it comes back. We got f of 4 equals 2, f prime of 4 times x minus 4, and in the original question, we can see, actually, there's no x minus 4 term in the original. So I can say that f prime of 4 must have been 0. In this next term, we've got the x minus 4 squared, and then the coefficient is made up of this portion of the numerator and the denominator, which means that f double prime of 4 all over 2 factorial somehow had to equal the -5 that was given. So if I multiply the 2 factorial, or really just 2, to the other side, I'm going to end up with f double prime of 4 must be -5 times 2, or -10. And then for this next term, somehow f triple prime of 4 over 3 factorial must equal +8. And so if I multiply 3 factorial, or 6, to the right side, I'm going to end up with the third derivative at 4 must be 8 times 6, or 48. Okay, so that's kind of working backwards a little bit. Just another creative way that Taylor polynomials can be used to solve problems. Letter B, does f, so our original function, does it have a local max, a local min, or neither at x equals 4? So we can use these derivatives to help us with this. We can tell that f prime of 4 equals 0, and we can tell that f double prime of 4 is negative. So when our first derivative is 0, we know that we have a relative extreme value. And when the second derivative is less than 0, that tells us that we are concave down. So the only way to have an extrema when we are concave down is if it's a maximum. So that is a property from Calc AB. We can say that f has a local maximum. And I'll say therefore at the beginning of that. Okay. Okay, one more question to go. Let's see what we got. The function f has derivatives of all orders for all real numbers x. We are given the function value and the first 3 derivatives when x equals 3. Write the third degree Taylor polynomial for f about x equals 3. So we have p sub 3 of x, and let's just start to fill this in. So we've got -4 plus 2 times x minus 3 plus 7 times x minus 3 squared over 2 factorial plus -5 times x minus 3 cubed over 3 factorial. And I'm going to do a little bit of simplifying here. So we get -4 plus 2 times x minus 3 plus 7/2 times x minus 3 squared minus 5/6 times x minus 3 cubed. All right, so there we go. There's our third degree Taylor polynomial. Letter B, write the fourth degree Taylor polynomial for g of x. So we don't know anything about g, except that it equals f of x squared plus 3 about x equals 0. All right, so this question is a little bit complicated. I'm going to show you the long version of the work that I don't expect you to write down, that I originally did when I was solving this question. And then we're going to talk about the simpler way to do this. So if I kind of just slide over here my key, you will see, as soon as the lag catches up to us, all of this works. So take a look. I started out with g of x equals f of x squared plus 3. I found the first derivative using the chain rule. So it was f prime of x squared plus 3 times 2x. Then I used the product rule and the chain rule to find the second derivative, and I did the same thing for the third derivative and the fourth derivative, which ended up being a ton of work, and you can take a look at all of that. That's on my page. Then I plugged in 0 for x, and that's what I did in one of these final lines down here. I did that for all the original g and the first 4 derivatives. So I found that the original function value was -4, and then I get a 0, a 4, a 0, and an 84. So then I plugged that into the Maclaurin polynomial formula, right? Because we're centered at 0. And it's simplified to -4 plus 2x squared plus 7/2 x to the 4th, which is the correct answer. However, there is a simpler way to do it, which I'm covering up here. So let me reveal it. And then this is what we're going to write down. If we take the answer from the previous question, which was the Taylor polynomial for f about x equals 3. If we're trying to find f of x squared plus 3 instead of f of x, what we could do is take that approximation that we already had and think about every place where there was an x, and we're going to plug in x squared plus 3 for every x, because that's what f of x squared plus 3 means to do, right? It means substitute in x squared plus 3 for every x. So if we do that for all 3 spots where there is an x, it just so happens that the plus 3 is going to cancel out with the -3 that existed because we used to be centered around 3. So then we end up with this simplified version of the approximation where the plus 3's and the -3's cancel and just leave us with an x squared and an x to the 4th and an x to the 6th. And if you think back to the formula, since there is no x minus 3 or x plus anything in parentheses anymore, we're now centered at x equals 0, which is what we wanted for letter B. And since we wanted the 4th degree Taylor polynomial, we currently have up to the 6th degree. So we only need to use the first 3 terms. That's why I have those first 3 terms boxed in. And what do you know? That ends up being the same answer that I got after all of this crazy amount of work that I did in this question. So what we're going to do right now is just copy down the shorter version of the work onto our own notes sheet, which I will do as well. And I'm going to try to explain what I'm doing as I go. So I'm going to substitute x squared plus 3 for every x in the approximation from above. So we end up with -4 plus 2 times x squared plus 3 minus 3 plus 7/2 times x squared plus 3 minus 3 squared minus 5/6 x squared plus 3 minus 3 cubed. And then let's just kind of simplify this a little bit. So the plus 3's and the minus 3's end up canceling out. So we get -4 plus 2 x squared plus 7/2. The plus 3 minus 3 cancels out. We have x squared squared, which is x to the 4th. And then we have minus 5/6. The plus 3 minus 3 cancels out. We have x squared cubed, which is x to the 6th. And since we only want the 4th degree, we're only going to need these first 3 terms. So the polynomial 4th degree approximation for g of x is -4 plus 2x squared plus 7/2 x to the 4th. It's kind of magical because we became centered about 0 automatically in this new question since the plus 3's and the minus 3's canceled out. But it works. All right, so that's the kind of shortcut we're going to be looking for. That's the way these questions are designed to be solved so that you don't have to do a ton of extra work to be able to solve. All right, so that's what we're going for there. And that was the last question. Hopefully that makes some good sense to you. Please let me know if there's anything I can do to make this more clear. And good luck with the worksheet. As always, Let me know if you have any questions. Thanks very much and have a great day.